so many people on a Monday morning. Okay, so today is the second talk of Bernadette. I reintroduce her for those who were not here at the time. So Bernadette is visiting here with his visiting program for history of physics that we are setting up. It's the first experiment in this direction here at the Coping. The aim of which is to have interactions between historians of physics and working physicists. This is part of a project Bernadette and I have been carrying out already for some years now with a series of symposia called History for Physics, and also a special issue of the European Journal of Physics Age that we are currently editing. Bernadette has received her PhD in Göttingen in mathematics, working on Wasserstein geometries and their application to quantum theory. And since then, she moved for a postdoc at the Max Planck Institute for the History of Science in Berlin, where she's still working. And last week, for those who were not here, she gave a meta talk, an introduction to the methods of history of physics and how these can be useful for physicists and how these can be mutually beneficial. Whereas today we will hear more about her actual work, research work in the history of physics. I take the last 2 seconds to also advertise and take advantage because Bernadette and I are both part of an association called Basic Research Community for Physics of Young Physicists Concerned with Foundations. And you will find these posters hanging all around also outside here because this weekend we are having a meeting of this association with public talks on Saturday and Sunday about the academic cultures and the publishing system. And so I invite you to have a look. There is a QR code in the corner of the posters. Please, Bernadette.
Thank you, Flavio. Okay, so maybe I'll wait a second until everybody has a seat. While we're waiting, let me say that I'm very happy that so many people came again today. So I'm very happy to see that. As Flavio said last time, I gave a more introductory talk about history of physics, about the subject. And my aim today is to give a bit more research-oriented talk about my research in the history of physics. And if you remember from last time, if you were there, I told you that we in Berlin, we're doing something that's called historical epistemology. That means that we kind of start with an epistemological question and approach this with historical methods. And this is how I would like to start today. I would center for today's talk an epistemological or historical epistemological question and start from there. So the topic that I would like to talk about today is actually related to a situation in contemporary physics, of today's physics, which is the, well, let's say, empirically difficult situation of some of the foundational theories we're working on today, currently. But it's actually not really the status itself that I'm wondering about today here, but it's more like the question, how were these theories developed, by which methodology, and how are they still being developed? And the term I want to coin for this is non-empirical methodology. And there were a few questions last time what I mean by this. And just to get a brief clarification, what is meant by non-empirical method? Well, first of all, a method is a way how to do something. For example, how to advance a theory or how to quantize a system. And a non-empirical method is well, as the name says, a method that is not related or not guided by empirical content by any means. But instead, it could, for example, be guided by an idea of how a theory could look like, or of an idea of how we think nature should be, right? And do I have some? Exactly. So examples for this are obviously, so the most obvious example for this is purely mathematical reason. If we forget ontological status of our theory and we just develop mathematically by arguing that certain objects have nice mathematical properties and therefore they should be used as fundamental objects, for example, in a theory, or because they are unique or anything related to purely mathematical reasoning. But obviously, it's difficult to really give a precise definition of what exactly we mean by a non-empirical method, and different people may have different opinions about what is non-empirical and what is not. For example, is a physical principle non-empirical or not? But for our case, it's totally okay to not give a precise definition, but just to have an idea of what we mean, because this is not a philosophical analysis. This is really just a start from where we want to do historical analysis. And so the question, the epistemological question that I would like to start with is, how did non-empirical methodologies become historically possible? And in order to understand this, I would like to introduce to you two case studies, two historical case studies, which is Leon Rosenfeld and Albert Einstein. And explain to you in which sense they have been used non-empirical methods already at that time, so that it's actually not a new phenomenon that we see today, but that's something that has been there before. And then the question is how, in those cases, it became historically possible. And finally, we would like to conclude with a short outlook or conclusion of how these two cases might have actually influenced our current non-empirical situation. So I would like to begin with Leon Rosenfeld. I can imagine that not all of you maybe have heard of him. He has been at that time a very important theoretical physicist, a Belgian theoretical physicist, but I think not everybody nowadays still knows him. So I give the lifetimes of Rosenfeld to have a vague idea. So he was born a year before Special Relativity came out and died in 1974. He was Belgian, and he is mostly known for his foundational work with Niels Bohr. They both have two very fundamental papers on issues of the measurement process in quantum field theory. And also at that time, he was one of the very fierce defender of Bohr's interpretation of quantum mechanics, and really made a name for himself as being kind of the spokesperson of Bohr's interpretation of quantum mechanics. But what is important for us today is that he was actually the first person to attempt a quantization of the gravitational field. That was in 1929. It actually came out in 1930. I don't know. Okay, so unfortunately it's not, you see it a bit blurred. the solution is not so great, but so the situation is that he didn't actually only give one attempt to quantize gravity, but actually he wrote 2 papers on this with 2 different ways to quantize. The first one is called Quantelung der Wellenfelder that you see here on the left. And the second is über die Gravitationswirkung des Lichts that you see to the right. And so I would like to tell you a little bit what he has done in these papers. And then you might be surprised to hear that afterwards he actually changed completely his mind about what he did and whether quantization of the gravitational field should actually be done. And we will hear some of his arguments of why he thinks that's something you shouldn't do. So let's start with what he did in this first paper, zur Quantelung der Wellenfelder. This is actually based on Hermann Weyl's paper from 1929. It's called Elektron und Gravitation. If you remember last time, I was trying to advertise a reading group where we're reading Weyl's 1918 paper, which is called Gravitation und Elektrizität. And maybe you remember that I kind of wasn't able to give the full title, but it's because they're really very similar, and I had some sort of superposition of these titles in my head, and somehow it didn't collapse. But for this specific paper, the first quantization of gravity by Rosenfeld, the relevant one is Weyl's 1929 paper. Which is basically what Weyl did, the innovative act of Weyl's paper, is that he proposed a way to couple spinors to the gravitational field by expressing the gravitational field not in terms of a metric, but instead in terms of a tetrad field. So a tetrad, for those who don't know, is a field of 4 orthogonal vectors that kind of the idea is to have at each point a coordinate system. And if you have these tetrads, this field of 4 orthogonal orthonormal vectors at each point, they give you a metric. You can define, starting from them, you can define a metric, and this is the metric kind of from which you go on to do the usual stuff that you do in general relativity. But once you have the tetrads, you can not only define a metric, but you can also find a kind of straightforward way to couple spinors to curved spacetime. To curved spacetime, or to kind of couple spinors on a flat spacetime so that they look like being on a curved spacetime. And based off this idea, Rosenfeld used Heisenberg and Pauli's methods from quantum field theory that they've been just devising in this very year to quantize the gravitational field. And it's not they did not quantize the metric, but they quantized the Vierbeiner, the tetrads. So that's the idea. And Rosenfeld got quite far in doing this. However, he did not succeed in writing down a fully canonical Hamiltonian. And he stopped right before that, and the only thing he had to do is to solve the constraint equations for the canonical momentum for the time derivatives of the fields. So that's the only thing that was left. So he was really close, but this he didn't do. So that's essentially what he did in his first paper. And then there was a second paper on the quantization of gravitation, which was, however, very different in nature. So while in the first paper he quantized the full nonlinear structure of gravitation, in the second paper it was actually a different aim. So the main motivation was to understand why in quantum electrodynamics, that was really being developed in the same year by Pauline Heisenberg, the self-energy of the electron is infinite. So there was an impression that something is kind of odd with the theory, and the idea was to understand if this is actually a truly quantum, a manifestation of something that's odd in quantum theory, or if this is maybe something that's actually classical and only comes out after quantization. So what Rosenfeld did was that he calculated the self-energy of the photon, or of an electromagnetic field, in its gravitational field. However, he found this to be infinite as well. And so for this, he did not quantize the whole gravitational field, but as you could maybe see here, he started with a linear approximation to an electromagnetic field and quantized this linear approximation. And then perturbatively saw that the self-energy of this quantized field also had an infinite self-energy. So that was very disturbing, because it seemed so that even in that case the self-energy is infinite, then this infinity must be something truly quantum. So something seems to be strange with the theory. Anyways, this is just to introduce to you what Rosenfeld did. So he did very foundational work. He was the first person to quantize the gravitational field, both in the full nonlinear case and also in a linear case. Unfortunately, none of these results were very pleasant. In the first case, he didn't manage to finish really the full quantization, and in the second case, he ended up with infinities. So after these papers, he never worked on this topic again. Actually, in this very same year, he moved from Zurich, where he worked with Pauli on those papers, to Copenhagen to work with Bohr. And from then on, his research attitude really fundamentally changed. And since our focus for today is the question how non-empirical methods became historically possible, I would like to give you a few quotes of Rosenfeld's estimation on how he saw the situation, of his judgment of what he did in these papers. So first of all, a bit more polemic quote maybe that he wrote in a letter to Bondi 30 years later. And he said that, "I think I could make a report on quantization of gravitation much shorter than 30 minutes. The full text of it would be, et ego censeo gravitatem non quantificandam esse," of vernacular words to that effect. So for those who don't know Latin, including me, I had to translate that. It apparently means that, and I think that gravitation cannot be quantized. And there was obviously a response to a request to give a talk on quantization of gravitation for a duration of 30 minutes. So that's what he thought, and that's, I think, also really displays Rosenfeld's character quite nicely. That's how he was. But he gave also less. I'm not saying he's polemic, but he was very sharp in his criticism. But he gave some more insightful arguments also on how he sees this endeavor. And one of this is actually 1 year later in lecture notes on quantum field theory, where he stated, there is no reason to think that this same method is likely to provide us with an adequate description of the interactions between material particles, or to express the same idea in other terms, that the concept of the photon, which immediately results from the quantization of the electromagnetic field, can be legitimately applied to the analysis of fields other than pure radiation fields. So, put shortly, the quantization method is something that kind of was extracted by the analysis, the analysis of the quantumation of the radiation field, that is the electromagnetic field, but should not be applied outside of this original realm. And he kept this opinion throughout his life. 30 years later, in that same year, we had the first quote from. He said, on a conference after a talk given by Bryce DeWitt, who, as you might know, also foundationally contributed to quantum gravity, he said, it's nice to have at one's disposal such exquisite mathematical tools as the present methods of quantum field theory, but one should not forget that these methods have been elaborated in order to describe definite empirical situations in which they find their only justification. Any question as to their range of application can only be answered by experience, not by formal argumentation. So my interpretation of his statement is that applying the quantization principle outside of empirically justified situations is nothing but a formal argumentation that is a non-empirical method, and thereby, first of all, means nothing really. And one can be lucky if some physical insight can be gained from this, but one should not expect, just because it worked previously in an empirical situation, that it will work when it's applied somewhere else with a non-empirically grounded argumentation. So this is why I would argue that this is an early situation of how formal, non-empirical theory development has been employed. And now one can argue, so why did Rosenfeld nevertheless do this, even though afterwards he said this is actually nothing you should really do? Or put in historical terms, how, back to the original question that we had, how did this situation actually become historically possible? So why, why did Rosenfeld do this in the first place? And then one can say, okay, because he just did it, but there's mostly also an historical answer to be given to this. Because things mostly don't happen contingently, and the historical reason why this became historically possible here is that the actual actor behind this is not Rosenfeld, but it's actually Wolfgang Pauli, who urged Rosenfeld to do these calculations. And Pauli was a very unique figure in that he was at home in several communities. So he was one of the main people for quantum theory and quantum mechanics and quantum field theory. But also, he actually started his career with working on general relativity. His very first research paper at the age of 19, before he started at university, was on general relativity, actually on unified field theory. So his upbringing, his academic upbringing, basically was in unified field theory. So he really, these concepts and ideas of uniting gravitation with the electromagnetic field and possibly more was really deeply ingrained in his thinking. This is the one branch, and then this is also how he even knew about Weyl's paper in 1929, and that he was even able to read this because many physicists at that time weren't able to understand general relativity. And so this unique blending of unified field theory background and quantum field theory background made it possible for these early papers on quantum gravity to appear. And I don't want to say that Rosenfeld has no agency at all, but I think that only in hindsight he really analyzed what happened there. So that's my first example of non-empirical methodology and how they became possible. Yeah.
So, non-empirical methodology, where we're talking about the last century, so for instance, I don't know, 2,000 years ago, 2,500, just make some arguments and said there must be something indivisible. She called it out, and that was also accurate.
Yeah. I'm not saying that this is something entirely modern or contemporary. This, I'm sure, certainly, this has always been employed in one or the other way. But what I mean is really the kind of non-empirical methodology that we're using today. How did they emerge? Like, where does this come from that we do what we do? This. Exactly, in the context of modern foundational theoretical physics. And I believe that it starts in these years when quantum field theory started to being developed. And this is the one branch, and the other branch is actually unified field theory. These two things uniquely come together in Rosenfeld, even though it's not so possible, not so obvious that there's a unified field theory background. But it's very obvious in Einstein. And this is actually the second example that I would like to give. So you all know Einstein. I thought to give an uncommon picture of his, where you maybe haven't seen him before. So we all know what he did. We owe him special relativity and general relativity, and foundational work on quantum theory. But what's maybe not known to everybody nowadays is that he actually spent a very large part of his life working on unified field theory. So I actually put also another picture. This is Einstein with Walter Meyer, and actually a Viennese mathematician who worked with Einstein on unified field theory. So we've heard the word unified field theory a couple of times, and now I would like to take a moment to say what exactly it is. So it's a classical field theory to begin with that's supposed to unify formally the gravitational and the electromagnetic field where, however, the gravitational field had the conceptual primacy. So you really start with the formalism of general relativity, and the idea is to work out ways how to bringing the electromagnetic field to the picture. But that's actually not all. The idea is also to reduce all properties of matter, like the quantum properties, but also that the discrete nature of matter, to properties of this unified field. So that's the idea, and surprisingly, even though it's a classical theory, the years when Einstein worked most intensively on this theory is when quantum mechanics was being developed, while everybody else thought this is the real game, Einstein worked on unified field theory. And just to give some statistics, he had more than 40 papers, which is roughly a fourth of his published work, and about half of his published scientific work after 1920. So he was really serious about unified field theory. So this is, I once wrote on a blackboard all the different kinds of approaches that Einstein tried to formulate a unified field theory. You can see that can I point? In principle, can distinguish between the 5-dimensional approach and an approach that's somehow a generalized geometry, generalized Riemannian geometry. And here you see a timeline. And the first thing that he really tried was Kaluza's 5-dimensional approach. He picked up his idea, and with his assistant Grommer, he did some stuff that didn't work out. The next thing was that he worked on actually Einstein's program for unified field theory Eddington's idea, and he had some really esoteric ideas, not to start with a metric, but with a Riemannian tensor. But this also didn't work out. I don't want to go to into the details of all the approaches. I just wanted to give you an idea of the amount of different approaches that he tried. It was also interesting that he often, after having given up a certain approach, that he came back to it. For example, in 1927, he came back to Kaluza's theory to try a few things. And he worked with different people, here with Walter Meyer, with Bergmann and Bachmann, on all kinds of really interesting ideas. And he continued. So the last idea that he tried until the very end of his life was actually an idea where he started with a non-symmetric G menu, with a non-symmetric metric. That doesn't mean antisymmetric, but non-symmetric, just somehow. That you can then decompose in a symmetric and antisymmetric metric. Hoping that with this decomposition you get both gravitational field and the electromagnetic field, but no, you didn't. But that's the idea.
Also, just as a side comment, also Schrödinger wrote did some research on unified field theory. Apparently, Einstein got very angry because then Schrödinger contacted some journalists in Dublin saying that, Schrödinger solved or physicists at Dublin found the word formula and solved everything. And then
Yeah. I mean, Einstein for sure was not the only one doing that. At some point he was the only one and the main actor. And after Einstein died, this whole research program basically died. I'm just focusing on Einstein here because he really is the main driving force of this field, and the way he pursued this, I think, gives an interesting historical lesson to learn. So, because what I think is obvious that the way he developed his unified field theories is, well, basically purely mathematical. You've seen, it was probably too quick of a glance to get an idea of really what these attempts were, but I can assure you that all of these attempts listed here are purely mathematical investigations. So what he did was really based on Riemannian geometry, to wonder how this geometry mathematically could be generalized such that those two fields, or the mathematical formulations of those fields, could be formally unified. So so he really relied on the physical content of general relativity and Maxwell's electrodynamics, but there was no further, no new physical insight, neither physical principle nor empirical data brought into the game to advance the theory. It was really, and so I would say that there were actually three main principles that guided Einstein for his theory advancement, and this was the idea of formal unification, the idea of logical simplicity, and the idea of completeness. And he would really advance theories such that these principles were satisfied, and he would dismiss theories which, well, were, for example, not simple or not complete. So it was really values for pursuit worthiness of a theory also, which were purely formal, as you can see, I think. So just to give you some actual quotes of his to illuminate a bit what I said, this is an article that Einstein wrote to the Scientific American in 1950, where he justified his work on unified field theory. And you can see here what I marked already. And he argues of why we advance theories in the first place. Why aren't we content with what we have? And his reasoning is that it's the striving towards unification and simplicity of the premises of the theory as a whole, which is the very reason to advance theories. So that's what he said. And understanding means, so you understand more than you've understood before if you have a more unified and more simple and more complete theory than you had before. Then a similarly important essay, if one wants to investigate these aspects, is this Herbert Spencer lecture at Oxford in 1933, much earlier, where he said, where he characterized himself as a man who spent his life in striving for the unification of knowledge. So he sees this as what he does in life. He fully identifies with unification of knowledge. And a bit further down, he said, our experience hitherto justifies us in believing that nature is the realization of the simplest conceivable mathematical ideas. So, just to give another quote in this regard. So, and also here one can ask, how did this become historically possible? And also here one can say, okay, well, he just did what he did. But not, yes, and not only. So Einstein thinking, even more than Pauli's thinking, was deeply rooted in the electromagnetic worldview. And so the electromagnetic worldview was only very briefly. It started by the end of the 19th century until 1910, roughly, and the idea was to reduce all physical phenomena on the electromagnetic field. So one can see quite clearly that Einstein's effort to construct unified field theory is not only his own ad hoc research program, but that it's a continuation of the development of ideas and theories from the electromagnetic worldview. And it's, if one reads how people thought of theories back in the days, back in the electromagnetic worldview, one sees that they've actually already thought about these terms for theory advancements like unification, simplicity, and completeness. This is nothing that Einstein came up with, but this is actually something what has existed before, and Einstein was only resorting to old vocabulary, which I think is interesting because completeness nowadays is something that is closely combined with Einstein as a criterion of pursuit worthiness, or something how he characterized quantum mechanics to be wrong, but actually it's not his word, so to say. However, there is something that is his. So what he did out of this, what existed already, is that he turned these, what I call elements of thought, into purified and idealized operators for theory constructions. So he really extracted these values and made them into operators for theory construction. And this is what made it possible for him to construct such purely non-empirical theories. And I think it's really important to keep in mind that what he really aimed with the Unified Field Theory program is to establish a realistic counter-program to quantum mechanics, and that these non-empirical values or operators were means to guide him through non-empirical terrain. And so it is this, again, this blend of tradition, contemporary situation in physics, and Einstein's own research agenda, which enabled the development of these, of the employment of these methodologies. So after having presented these two examples of non-empirical methodologies, I would like to briefly ask if any of this had an influence of what we see today. Well, I think that unified field theory, and particularly Einstein, had influence on two research brands that started out as research directions being really on the fringe of foundational physics, which is quantum foundations and quantum gravity, but nowadays they're really part of the mainstream of foundational physics. And the influence of quantum foundations that was mediated from Einstein, I think, is quite obvious. And it's less obvious how unified field theory and Einstein actually kicked off or made possible, even in a sense, the development of quantum gravity. And this is my grander historical hypothesis that I'm currently working out, that all herds, all germs of quantum gravity that have existed actually had a direct influence from unified field theory and Einstein. So it was, even though it looks like something really different, the quantization of gravity really looks like it has nothing to do with unified field theory. It's very surprising to see that there was a strong influence of unified field theory, a classical research program, which made this quantum gravity program possible, I would say. Yeah, so these were all the arguments that I wanted to talk about today. And I thank you for listening, and I'm happy to take your questions.
So I never quite understood why he was not why Einstein was not just satisfied with coupling the electromagnetic field, perhaps even also electrons, to gravity, the canonical way, let's say, just taking the energy momentum tensor and saying that its source is g mu. So was he not aware of this paper by Hamann Weil, Gravitation und Elektron, or?
You mean the paper from 1929?
Yeah.
He was surely aware, but I think that, so what he ultimately wanted is to have all the quantum properties of nature and particle properties of nature to get them for free at the end, so that you have particle solutions, or solutions of the unified field that look like particle solutions, or that look like particles that have quantum properties. That was his, that's what he thought how it should be, and that's actually an idea that really started in the electromagnetic worldview, where people really tried the same thing, just not with the gravitational field, but with the electromagnetic field.
Thank you, Bernadette. So, okay, trying to understand also this business of yours with respect to the previous talk, alright? So, you posed the question, how did this become historically possible? I'm not sure I understood what's the answer you gave to that.
So I've tried to split up the answer for the grand question, how the contemporary situation became historically possible, by first investigating two historical examples to, well, on the one hand, try to learn from them how non-empirical methods in general can be employed, how it can look like, then to understand how they became historically possible, and also, and this is still a vague outlook, admittedly. I mean, this is a big question. How these examples may have been responsible for what we see today. So that's the logical structure.
So, what do you think is the answer? Do you think it's because Einstein had such a big, weight that he had this idea of, let's think about, I don't know, mathematical elegance, completeness, or is it other developments of the era or cultural context that made it possible?
Yeah, I think so. There are several answers, as always. So as I said, I think the main research programs that many people are investigating today, which is quantum foundations and quantum gravity. And I think for this purpose, excluding string theory from this. You can really see, how there's a tradition that goes back to Einstein's thinking. So it's not necessarily that it's a conscious thing that people relate to Einstein. I don't think anybody in quantum gravity is aware of the influence of unified field theory on their program that was mediated in a not necessarily obvious way through Einstein in several ways.
So you're saying that there is, although everybody knows Einstein, there is something that was forgotten, which was somehow that this non-empirical methodology we're employing has to do with the unified field theory. Method starts there, which then sort of fade and died, and you're pointing that out.
Yeah, exactly. Yeah.
Give the word to myself.
Yes.
Can you explain a bit better? So your last slide, the influence on today's research. What do you exactly mean by the influence it had on quantum foundations? This program, because I see quantum foundation as the most empiricist approach of
yeah.
theoretical physics.
For sure.
So I see that in quantum gravity or string theory was this non-empirical aspects of simplicity.
That's true. That's a good point. So with my statement, I didn't want to say that I believe that quantum foundation is a non-empirical business. First of all, I just wanted to say that there's an influence. It does seem to be the case for me that in quantum foundation, the theory development is still very formal, and I think that there is some points to be made if one would investigate this, which I haven't done. But I think that there is some things to find and some points to make there. But I don't feel ready to really make a statement as of now. But I do believe that yeah. Yeah.
Thanks for the talk. I would like to make a comment that very often we are forced in this non-empirical methods or periods of non-empirical methods. Non-empirical is the prime example of that because there are no empirical evidences of that. But very often these are, when we start this and non-empirical ideas to develop, we are very much influenced by the empirical experience thus far. And so, even as you nicely expressed this Einstein work on the unified field theory was a reaction on the empirical evidence of the quantum theory that he wasn't pleased with. And so, I wonder whether this, after all, dichotomy that I very often hear nowadays between empirical and non-empirical is useful in a sense, and whether we should see this more relaxed and combined. And the second thing is that indeed we then in these non-empirical periods or non-empirical methods follow the idea of unification of knowledge and symmetries and simplification. But also it's very important from where we start, which is related to our empirical experience thus far. And I think, as you noted this, Einstein built up on this pre-quantum understanding of unification of knowledge. And the post-quantum unification of knowledge would be completely different. It seems to me that these elements are kind of decisive then for progress in these dry periods.
Yeah, exactly. I mean, what Weihe did in his 1929 paper was, I think, to give an attempt of a post-quantum or quantum interpretation of the classical unification program by proposing a way to couple spinors to curved space-time. I think that was an idea to, and this whole business was then supposed to be quantized. But yeah, that wasn't extremely fruitful. Yeah, but yeah, I guess there maybe a really good idea still needs to be found.
I think a fun question to ask is whether operationalism is empirical or non-empirical for this project.
What do you mean by operationalism?
I'm not the right person to ask that question.
Okay. Well then, then I think I don't know what to answer. Yeah.
So the famous definition by like in his Richardson textbook, which uses Einstein. It's funny, there's like two Einsteins, right? Late Einstein and early Einstein. They're like really strong conflict with each other in how you want to interpret them. And early Einstein, people took that and run with it into this theory of operationalism. And then there's late Einstein, which is exactly presented now. So I'm very interested to answer the question, which is why I've jumped in. So Bridgman in this book, when assessing the early work of Einstein, gives the definition of imperialism as a whole different thing. Operationalism as the definition of concepts and notions according to the actions of one another. So an object is the totality of its effects, so to speak. So you know, in time is that which is measured by clocks, say. The distance is that which is measured by rods, and so on and so forth. This is kind of the idea of operationalism.
Oh, that's what you mean. Okay, so really the operationalism in quantum mechanics, right? So
It doesn't have to be quantum, right?
okay, but that's so okay, but yeah, I get it. So okay, the question is if that's empirical.
I can explain it. That was a bit of a joke, but what I mean is that you know, for instance, in this institute there is a huge tradition, what is called operationalism in quantum foundations, which comes, I mean, without wanting to put words in the mouth of anybody, but sort of there is this experiment that multi tables. This gives you an interpretation of mathematics that is adapted to what's happening in reality, but then you have also very abstract theoretical analysis of phenomena that are way beyond the realm of what you can reach in the lab, which is the method applied by many here. Maybe it doesn't fit the box, but I'm wondering if you would categorize that. Let me give you an example. For instance, just like it's doing quantum reference frames and system of operation, but some of these phenomena are way beyond empirical reach. So I don't know if we would call this empirical or non-empirical.
I mean, well, I mean, as I said, I'm not the person to give a precise definition, and this is really open to debate, and that's probably a question for philosophers, which I'm not, and it is still an interesting question, and I'd be interested to think more about it, because I think analyzing this really always helps to understand what's going on, and so, I mean, I'd be happy to talk about this. Yeah, I'd be very curious to think about this. But I can't answer this from, as of now.
Yeah, it was a suggestion.
Yeah, but.
But isn't it isn't it strange that he, in this Scientific American article, Einstein was referring to Mach, saying that we should seek for mathematical unity in our description of nature. But isn't that very non-Machian in a way? Because Mach thought, for the way I understand it, of laws of nature as basically just abstract correlations between observations, or observational effects. So
I mean, what Einstein was referring to there was Mach's idea of an economy of thought, that the way you think about nature should be very economical, and in particular, you shouldn't think in terms of redundant or, well, in terms of, well, in a non-positivistic way, because if you had concepts that don't directly relate, it's not very economical. So that's what he related to.
I was just wondering if you also consider this question like together with philosophers, because it seems like from the discussion so far and also in general, I mean, the whole notion of what it is to be empirical and non-empirical is a fully philosophical question. So is there any collaboration?
So I'm trying to collaborate. So I've reached out to philosophers who philosophize on these terms, and let's see. But I would like to, I think that could be useful indeed.
I have a bit of a difficulty understanding the difference between empirical method or non-empirical method. No? So I just asked a question. So for example, imagine that one of these approaches of Einstein would have worked.
Would have worked?
Yes, and it would have given you like a beautiful theory working and describing everything.
Yeah.
Would this approach be a non-empirical method anyway, or not?
Yeah, I mean, so I would say that he reached something empirical by the employment of non-empirical methods. That's how I would see it. I mean, you can, of course, still be lucky, right? You can get right things. I mean, I'm not saying, I'm not judging in any case. I'm really just trying to observe and of course you can achieve something physical if you apply non-empirical methods. That can happen, and but it's still, I would still say that the way you got there would then be without empirical guiding.
More of a historical question, in the sense that, like the question was, the epistemological question was like, how did these modern empirical methods become historically possible? But then we kind of always spent like time in the early 20th century and went up to today. But these people, when they actually employed these non-empirical methods, they already had a history behind them. So is this also part of your research program, to kind of look at how do you actually reach this point?
Yeah. I mean, I've tried to actually talk about this because, so if you remember, so after each of those two historical examples, I've tried to give a short analysis of how those examples became historically possible. I think that's very relevant and very interesting, definitely.
Especially Mach kind of was like, in a sense, kind of the anti, or like as an actor, like anti non-empirical methods, no? Like he basically put it in Boltzmann for his theory not being empirical to some extent.
Yeah, he was. That's true.
I would like to show up something that maybe is relevant to you. That so as you know, many physicists, when you talk about method, have been very much influenced by the Popperianism and falsificationism. It's kind of how it's naively described how science progresses and is known in the physics community.
Yes.
Or in the scientific community. And it should be noticed that Popper himself, he got acquainted very early with Einstein's general relativity, thanks to two friends of his, Arthur Mach, who was a physicist, a friend of Schrödinger, also here in Vienna. And he acknowledges explicitly that his Logik der Forschung, when he develops the idea of falsification, borrows a lot from the development of the theories of Einstein. So because for him it doesn't. So he was not an empiricist. Clearly, he's not an empiricist comes from, it says that science progresses by both conjectures and refutations. So it doesn't matter where the idea comes from, it only has to produce empirical statements to be tested. And so this idea of non-empirical methods as a way to develop a theory, I think it goes a lot also through Popper. It could be that also this has an influence in the scientific methodology. So it's not, it was opposing the Machian idea that we only have data and we organize them. So science, what does science is organizing them in the most economical way. You don't start with empirical data. It was an anti-inductivist. They would say you start with both conjectures. You start with ideas. These ideas are theories, are mathematical or statements in natural language.
But the conjectures that Popper had in mind still somehow, so the aim was still that those conjectures should be testable, right? That
exactly.
They should.
So somehow
but that,
split this into the, there is the context of discovery and the context of justification. So the discovery,
of these conjectures, you mean?
Was part of conjecture and it was non-empirical, going through, because it was directly acknowledged by him that this idea got it from Einstein. Einstein went to the, well, and GR somehow is indeed like this, right? So GR starts from developing this abstract mathematical ideas, and then it produces
he did
testable statement of
not quite. So it's, for the that's what Einstein thinks how general relativity came out, but how he developed it. But there was some, people misremember things, and actually Jürgen Rehn, our director, he did a lot of work on Einstein together with other historians. They found that it's not true. He did not develop GR in that way, because what was very important was that, he devised physical principles that were guided by his intuition and continued to guide the development of the theories. And those principles were empirically meaningful, so they had direct relation to the physical world, and also quickly gave testable predictions. So as for the development of GR, this was really different than from unified field theory, because there he completely left out the physical principle part. Thanks a lot.
Bernadette will be here in the Institute until the 19th.
19th.
So I encourage you to interact more with her